Hello friends, in this video we are going to discuss about the Gunn Diode. So starting with the Gunn Diode, the first point that we can say that it is a junctionless diode. Junctionless diode means that no p-n junction will be present inside the diode. Now, this diode was first discovered by scientist J.B. Gunn in 1963 in the IBM laboratories. So, the operational principle in which this diode operates, so you can write that operates on the principle of Gunn effect. The operational principle is the Gunn. We will discuss briefly about this Gunn effect. Now, generally, what happens? The Gunn effect is a special phenomenon that occurs in the semiconductor, but if Gunn diode do not have a junction, then what does the Gunn diode constitute of? The Gunn diode constitutes of metal semiconductor junction, and this semiconductor that is used for this metal semiconductor junction are generally N-type gallium arsenide semiconductor is used for metal semiconductor junction. Not only gallium arsenide but also cadmium telluride. Another material is indium phosphide is also used. Either we will use gallium arsenide, cadmium telluride and indium phosphide. Now all these semiconductor materials are direct band gap semiconductor. So we have to use direct band gap semiconductor and metal junction for fabricating the Gunn diode. So let us see how the fabrication of the Gunn diode looks like. The fabrication of the Gunn diode looks like this. There will be a semiconductor. So let us take a N-type gallium arsenide as the semiconductor, and above the N-type gallium arsenide there will be a metal layer. This is the metal layer on the above of the gallium arsenide, and from this we will take out a contact. Similarly, at the bottom of the semiconductor there will be a metal layer like this, and this metal layer will provide another terminal. This is the another terminal. Now this is the metal, and this is also the metal, and this total thing is a Gunn diode, and this Gunn diode generally works on the principle of Gunn effect. So let us see what is Gunn effect. Gunn effect. So Gunn effect is some phenomena where we know above. Gunn effect is defined like this: above some critical voltage corresponding electric field of amount of the electric field is like that 2000 to 4000 volt per centimeter. The current in the every spectrum, current in every spectrum of gallium arsenide semiconductor becomes a fluctuating function of time. In this Gunn effect, the statement states that above some critical value corresponding to the electric field of 2000 4000 volt per centimeter, the current in every spectrum of the gallium arsenide becomes a fluctuating function of time. So let us understand this. What does it mean? To understand this, we have to go for the direct and indirect bandgap semiconductor. So in the direct and indirect bandgap semiconductor, we have already discussed about that. So let us see how we can understand this Gunn effect. So as our previous discussion on the Gunn effect on the part 1, we have seen that this is a Eke band diagram. So this is the first Eke band diagram, and this Eke band diagram is for the direct band gap semiconductor like gallium arsenide, cadmium, telluride, indium phosphide, all are direct band gap semiconductor. In this case, we have plotted, you can see, we have plotted energy in the y-axis. This is the kinetic energy that we have already discussed in the Gunn diode part 1, and in the x-axis we have plotted the k vector, that is the wave vector, and this will be a direct bandgap semiconductor because the EC value, this is the EC value, and this value is the EV value. So maximum value of the valence band, this is the valence band. So maximum value of the valence band is EV, and minimum value of the conduction band is EC. Both of them are offering at same value of K. That's why it is a direct bandgap semiconductor. Similarly, in the figure 2, this is the second figure. This was the first figure. In the figure 2, you can see it is a indirect band gap semiconductor. And in this indirect band gap semiconductor, we know silicon, germanium are the indirect band gap semiconductor, where we know that the maxima of the valence band, this is the valence band, and this is the maxima of the valence band, which is denoted by EV, and the minima of the conduction band, which is denoted by EC. What they are occurring at different value of K, because EC is occurring at this value of K, but EV is occurring at this value of K. So this is a indirect band gap semiconductor. Now for the fabrication of gallium arsenide, we have to use this direct band gap semiconductor. We cannot use this indirect band gap semiconductor. That means this indirect band gap semiconductor is no use for the case of gallium arsenide. So let us see some detail about this direct band gap semiconductor. The practical Ekeeda diagram of a direct band gap semiconductor looks like this. This is a approximate picture. Actually, the picture of the Ekeeda diagram will of a direct band gap semiconductor looks like this. This is the practical or original picture of a decay band diagram for direct band gap semiconductor. So we can say this figure is the EK diagram for direct band gap semiconductor. In this EK diagram, we can see that there is a EC. This is the EC value, that is the minima of the conduction band, and this is the EV value, that is the maxima of the valence band, and in between this there is the EG gap. This is the band gap of the semiconductor. Now in the conduction band, we can see, if I look at the conduction band, then the conduction band looks like this. So this is the total conduction band of the decay diagram. In this conduction band, we can see that the conduction band constitutes of two values. The first value is the gamma value, this one, the gamma value, and this is also called the L value, and this is the X value. Generally, the gamma value, that is here, gamma value is sometimes called as the central value. This is the central value of the Ekeeda diagram conduction band, and the L value or the X value are called the satellite value. Satellite. So from the central value, we can see, if I draw the central value, so the conduction band looks like this. This is the conduction band, where this is the satellite value. So this is my L value, this is my gamma value or central value, and this is the X value. Now, if I look at these values, then we can see that if I see the satellite value, this is my satellite value, and this is also my satellite. In this satellite value, we can see that the curvature, this is a parabolic plot. So this is a parabolic plot, and in this parabolic plot, we can say that the curvature is less here. But if we talk about this central valley, so this is our central valley, you can say central valley. So in this central valley, we can see the curvature is high in comparison to the parabolic valley. So the most important conclusion that we can draw here, that the curvature of central valley is greater than the curvature of satellite valleys. This is the most important conclusion that we have to note from this practical Ekeeda diagram. Now we'll use this information in the later cases. So let us see how this information can be used to understand the Gunn effect. Now, to understand the Gunn effect, we have to understand the two value model that we have already discussed right now, that according to the energy band theory and the Eke band diagram, a n-type gallium arsenide, we use n-type gallium arsenide. Since the n-type gallium arsenide is a direct band gap semiconductor, so inside the Eke diagram of a n-type gallium arsenide, there will be a conduction band, that is Cb, and this conduction band has values. We have already seen that. First one is the central valley that we have discussed just before this, and the second one is the satellite valley. And the curvature, we have seen that the curvature of central valley, this one, is greater than the curvature of satellite valley. Now, we also know that the effective mass, if we think about the effective mass of the electron, effective mass of electron, and if we denote it as m e star, so this m e star depends on this equation, that is h r square divided by t2e by dk square. So this equation gives the effective mass of the electron. But what is this d2e and dk2? This thing is nothing but the curvature of the parabolic Ekeeda diagram. So from this equation we can say like this, that the effective mass of the electron is inversely proportional to the curvature of the values. So we know that since the from this information we can see that the curvature of the central value, if I write this this way, so C means the curvature of the central value is denoted by C sen, and the curvature of the satellite value is denoted by C satellite for sat. Now, since the effective mass of the curvature, but since the effective mass of the electron is inversely proportional to the curvature, so we can say the electrons which are inside the central valley, that is Me star at the central, and Me, that is the effective mass of those electrons which are at the satellite valley. In this case, that the Me star satellite will be greater than the Me star of the central. That means from this we can conclude in this way that like this, that is the effective mass of electron residing at the central valley will be smaller than the electrons residing at the satellite valley. So this information can be plotted like this. So far we have seen that if this is the energy, if we plot energy in this direction, that is the kinetic energy, and if we plot a wave vector in this direction A, then the plot will look like this according to the Ekeeda diagram. So the plot will look like this type, and there will be valence band also, and the valence band will look like this. This is the valence band. So we can see this is a direct band gap semiconductor, and this is the conduction band, and this is the valence band, and this energy is the EV energy, and this energy is the EV energy, or the difference between This two energy level is the forbidden energy gap Eg. Now we can see that this is the central level, central valley. This is the satellite valley. This is also satellite valley. Now suppose we have some electrons here. So these are the electrons suppose. Now suppose these are the electrons that are residing in this central satellite valley. Similarly, we'll have some electrons here in the central valley. These are the electrons of the central valley. Now these electrons suppose has some mass, effective mass, m star, and they are residing at central. And suppose this electron will have some effective mass, m star, and they are residing at the satellite valley. And according to the previous discussion, we can see that the effective mass of the electrons in the central valley will be smaller than the effective mass of the electrons at the satellite valley. So the mass is reducing for the electrons at different places. Now suppose if an electron goes from the central valley to the satellite valley, if there are, suppose this electron is moving some way to this satellite valley. So when it was in the central valley, its mass was very low. But when it goes into the satellite valley, effective mass will increase. Since the effective mass increases, so we can say that the velocity, that is the drift velocity of the electron at the central valley will be greater than the velocity of the, that is the drift velocity of the electron at the satellite valley. So the drift velocity also changes with this effective mass. A particle, an electron which will have less mass will have greater velocity, and a particle or electron will have greater mass will have less velocity. Since the velocity changes or the drift velocity changes if the electron transferred from the central valley to the satellite valley, then we also know that the drift velocity Vd equals to mu into E. If the drift velocity changes, then the mobility also changes. That means the mobility value of the electron, that is mu n, at the central valley will be greater than the mobility value of the electron at the satellite. So this thing is very important with respect to the Gunn effect, that when an electron will transfer from the central valley to the satellite valley, then its mobility will decrease. That means in the central valley, the mobility of the electron is high, but at the satellite valley, the mobility of the same electron will be lower because the drift velocity is for a particular electric field. Now, this information can also be used inside the Gunn effect. Now, if we draw the Gunn characteristics, then it will look like this. That is, we have told that according to the Gunn effect, that after some value of the electric field, the current in the device will become oscillatory. That was the Gunn effect. Now, if we plot the current versus current versus voltage, applied voltage characteristics, then in the y-axis I am giving current and the x-axis we are giving the voltage. According to the Gunn effect, it was told that after some certain value, let us assume that this is the applied voltage V1, after which the current will become oscillatory. So let us denote this as V1. That means V1 voltage after the current, this current value will be oscillatory, and it will look like this. From 0 voltage to V1 voltage, the current will increase linearly. So it will increase linearly, and after the V1 voltage, the current will become oscillatory. So it will become oscillatory after the V1 voltage like this. And this oscillatory nature, this one, will have some period of oscillation. So generally the oscillation time here for this periodic nature, so the oscillation time for the Gunn diode after the V1 voltage for the current oscillation is generally of the 0.222 millisecond. And if you see the oscillation frequency of this oscillatory nature of the current after the V1 voltage, it will have 4.5 gigahertz. That means we are giving some DC voltages to the Gunn diode, but after certain V1 voltage, the current that we are getting to the device is oscillatory in nature, and the frequency of the current that will flow will be 4.5 gigahertz. So this period of oscillation and the frequency of this oscillation, we can say that period of these oscillation depends on the transit time of the carriers, that is the electron, through the length of the device. So from this we can see that the period of oscillation of this part depends on the transit time of the device. Transit time of the carriers, the length of the device. Transit time means we have seen that the structure of the diode was looking like this. We will have a n-type gallium arsenide. This was n-type gallium arsenide, and on the two sides of this n-type gallium arsenide, there will be a metal layer like this, and there will be some metal contact. Similarly, here will be a metal contact with the n-type gallium arsenide. These two will provide the metal connection. So this yellow color is the metal. Now, when the electrons, if we look for the electrons will traverse in this direction if we apply positive potential here and negative potential here. So if this length of this semiconductor is L, and if the drift velocity of this electron is Vd, then the transit time, you can say transit time of this electron or charge carriers through the length of the device will be L divided by Vd, and this L divided by Vd will control the period of the oscillation of the current after the V1 voltage. This is the main theory of the Gunn effect. Now, why it is happening like this? After the V1 voltage, why the current is oscillatory in nature? For that, we have to plot the velocity versus electric field for the different material. So let us understand why this current is becoming oscillatory in nature after the certain voltage V1. So for that, let us describe with terms of drift velocity. So if I plot the drift velocity with respect to the electric field, so if I plot the drift velocity with respect to the electric field of the carriers, so let us assume that this is the drift velocity axis and this is the applied electric field. So I am denoting here it is Vd, the drift velocity, and in the x-axis this is the electric field, and let us assume that this is the kilovolt per centimeter in unit, and the unit of the drift velocity is meter per second. But start. Now this plot, we will plot this Vd versus mu for different materials like this. So if we plot for silicon the drift velocity and the electric field, we know that it will look like this. It will increase linearly first, then at some value of electric field, this value of Vd will become constant. So this is for the silicon material. But we will use as n-type gallium arsenide, and the n-type gallium arsenide as the plot look like this. In the n-type gallium arsenide, the electric field and the drift velocity plot will look like this. The drift velocity will increase linearly with the electric field. After certain value of the electric field, it will decrease in this fashion like this. So we can say this is for gallium arsenide. So we can say here that after certain value of the electric field, the drift velocity is decreasing. So let us assume that after E1 electric field, where the drift velocity of an n-type gallium arsenide is decreasing here. So let us see why it is happening. So according to the energy band diagram or the Ekeeda diagram, we know that if we draw the Ekeeda diagram of an n-type gallium arsenide, it will look like this. So in the Ekeeda diagram, we have already seen that when we have applied voltage of E1, in that case, the if we draw the electric Ekeeda diagram like this, so let us discuss this thing why it is happening in terms of the Ekeeda diagram. So according to the Ekeeda diagram, in an n-type gallium arsenide, the Ekeeda diagram looks like this, and there will be a valence band also. This is our valence band. This is the valence band. This is the conduction band, and we can see that this is our E P and this is our EC. Both of them are occurring at same value of K, because in the x-axis we are plotting the K and in the y-axis we are plotting the kinetic energy of the electron. And as we have discussed earlier, this is our central valley, and this is the satellite valley, and this is the satellite valley. So when the potential or the electric field is at E1, in between this, we can say that when the electric field is between 0 to E1, then at that case, more and more number of electrons, that is all the some or more and more number of electrons are accumulated here. So there is, as we increase the electric field from 0 to E1, so more and more number of electrons are getting deposited in the central valley. So as more and more number of electrons are getting deposited here, so we can say that for this case, the shift velocity will increase because we are increasing the electric field, and due to this electric field, the electrons are getting excited to the central band. That's why we are getting this type of plot. It is linearly increasing, and after E1, what happens? These electrons, which are in the central band, now are going into the satellite valley. So more and more number of electrons are now getting here from the central valley. So after E1, we can say that electrons will be transferred from the central valley to the satellite valley. And then what happens? We know that the mobility value of the electrons at the central valley will be decreased, and the mobility value of the electron at the central is higher. So when the electrons will be transferred from the central valley to the satellite valley, then the mobility of the electrons in the satellite valley will be decreased. If the mobility decreases, then the Vd velocity also decreases. That's why we are getting this plot. So we are getting that the drift velocity is decreasing because electrons are transferring from the central valley to the satellite valley and the mobility decreases. We have already started that. Since the mobility decreases, so the current will also decrease. That means we are getting a negative value of current, negative resistance. So in this region, we will get a negative resistance value. And due to this negative resistance, we will have a microwave frequency generation. So we can say that when in a negative resistance area, the voltage and current will be out of phase. Since the velocity is decreasing with the electric field after the E1, so the voltage and the current will be out of phase. So let us note down what has happened. So after E1, the negative resistance area occurs, and in this negative resistance area we know that the voltage and the current will be 180 degree out of phase. So if we recall the conductivity of n-type material is denoted by sigma n. Sigma n is the conductivity of this n-type gallium arsenide, and in this n-type gallium arsenide we can say the total conductivity will be contributed by the electrons from the central band as well as from the satellite valley. So let us denote the conductivity due to the electrons of the central valley is sigma c, and the conductivity due to the electrons of the satellite valley is sigma s. So sigma n can be written as q into mu c into nc plus mu s into ns, where mu c is the mobility of the electron which are in the central valley, and mu s is the mobility of the electrons in the satellite valley, and nc is the concentration of the electrons inside the central valley, and ns is the concentration of the electrons in the satellite valley. So if we do the partial derivative, then we can find d sigma by de. So after doing this partial derivative, we can find that the equation will look like this. That is, after doing the partial derivative, then the equation will be like q into mu of c into dnc divided by de plus mu s into dns divided by de plus q into nc into d mu c divided by de plus ns into d mu s divided by d. So this equation will give d sigma by de is nothing but the differential resistance. This is the differential resistance of the Gunn diode. Now, according to the Ohm's law, we write according to Ohm's law, we can write that J equals to sigma into. So, if I do dJ by dE, that means if I derivative the J with respect to the electric field, then it will be sigma plus E into d sigma by. Now, if I combine these two equation number 2 and this equation 1, if we combine this, after combining the equation 1 and equation 2, we can write, so combining this equation 1 and equation 2, we can write the equation like this: 1 by sigma into dj divided by dE equals to 1 plus d sigma by dE and sigma by E. So this is the equation that we'll get after when we combine the equation 1 and equation 2. Now, from this equation, we can say that the negative resistance will occur when d sigma by dE divided by sigma by E, this term will become minus less than 1. So then I will get the negative resistance will occur in this. Now, if I say when the negative resistance occurs, then what will happen? Then we can say that the energy difference between the two valleys, that is the central valley and the satellite valley, must be several times the larger than the thermal energy. That's why the electrons will only move from the central valley to the satellite valley when we will give a temperature, we give a energy from the outside rather than temperature. That's why we have to give the voltage to the Gunn diode. So in the Gunn diode, we can see that this occurs when the electrons will be transferred from the central valley to the satellite valley, and at that point we have seen that the Gunn diode current will be of oscillatory in nature and the oscillation frequency of the gigahertz. So this is all about the Gunn diode, and before ending this Gunn diode, let us see what will be the original structure of this Gunn diode. The original structure of a Gunn diode looks like this. is the original structure of a Gunn diode. From this structure, you can see that this is a Gunn diode original structure, and in this Gunn diode, you can see that this part is the Gunn diode, and this is the cross-sectional view of that Gunn diode. This is the bottom view of the Gunn diode, and this is the top view. So you can see there is a layer here. This layer is the metal layer, and in this metal layer, you can see there is a n-type gallium arsenide, n-type gallium arsenide, and in the bottom there is a gold plating. There is also a metal layer. So this is the original structure of an Gunn diode, and these structures are taken using scanning electron microscopic picture. These are originally scanning electron microscopic pictures of a real life gallium arsenide Gunn diode. So this is all about the Gunn diode. In this Gunn diode, we have seen that it is giving us some microwave energy when we will give a DC voltage. Thank you.